In this section, we're going to try and come up with methods of evaluating limits faster. Because even with the use of a calculator, coming up with a table or a graph, it can be time consuming in order to evaluate a limit. So if you'll recall, in the previous section, we sort of touched upon a principle that was really useful here. If the limit function is continuous on a small interval around the indicated point, then the limit and the function agree at that point. So I guess what I'm saying is, in a bit more easier tone here, is the function itself, if it exists at the point you're interested in, then chances are all you need to do is just evaluate the function and you're all set. So there's really no need to do a limit. So for instance, we saw the example 4 minus x squared, which you can use your calculator to do. I'm going to do a little bit faster in the program I was using so that we can move this along. So the limit from the left, as x approaches 1, we would need values for 0.9, 0.99, 0.999, and the limit from the right, we would need values that are slightly larger, but then getting closer to 1. So feel free to fill in these values from the program. So you can see the values as x starts at 0.9, which is on the left-hand side, and approaching 1 as we get to 0.999. We're really close to 1. The function itself is approaching 3. Okay, and we can see that also through the left-hand limit this way. As we allow x to get closer and closer to 1, the y values get closer and closer to 3. And even if I zoom in on this region really far, try and zoom in as much as I can, and I try and get really close to 1, I still get values that are really close to 3. And the thing is, if I actually get to 1, it's not undefined, and I can actually evaluate the function there and come up with 3. So what that means is this function is continuous, and if it's continuous everywhere, then that means at x equals 1, then around this value, we have y values that are defined. So that means the limit from the left and the limit from the right are defined. So because this point exists, it sort of implies that the limit value exists as well. And that's sort of what we're working with here. So if I have a continuous function, if I just plug in the limit value and evaluate, then I get the value of the limit, because what we observed from the limit value is the limit from the left was approaching 3 and the limit from the right was approaching 3. Since all of that was defined and I had a continuous function, this all works out and I don't actually need to go through the limiting process. So it makes a lot more sense to simply evaluate your function first and just see if it exists, and if it does, then move on. You don't have to go through the limiting process. Now, limits have a lot of properties, and we're going to establish these limit laws first before we jump into some examples. The gist of all of these properties is basically that you can just do exactly what I said. As long as you're working with a continuous function, you plug in the value that you're interested in. If the function exists, then the limit exists and you're done. So the different properties we have here, f of x and g of x are defined for all real numbers x, which are not equal to a, which is going to be our limit point. Then we let L and M be the values that we're approaching as we get closer to a from the two individual functions. The first property is a sum and difference law. So the sum of those two functions, if we take the limit of the sum of those functions, that's the same thing as taking the limit of each function separately and adding or subtracting them, and that doesn't affect the limit itself. The same thing is true with a constant multiple law. You can take the limit of some constant multiple of a function, or take the limit of the function times a constant multiplier. It doesn't affect the limit. There's a product of functions law, a quotient law. The only thing you have to be careful with the quotient law is division by 0. But then you have powers, work fine, roots of any order work fine. So pretty much as long as you can evaluate the function at a particular point, then the limit exists. Also, these two basic limits are always true. So the limit as x approaches a of x is just equal to a. So you just plug in a and you get, the limit value. The limit as x approaches a of some constant is equal to the constant because that function's never changing. All right, let's take a look at how these might work, and then I'll show you how they're actually used. So first off, use the limit laws to evaluate this limit. Okay, so we have a polynomial. The limit laws are basically saying this, that I can do the limit of any terms that are added, subtracted separately. So this would be the same as doing the limit as x approaches 4 of the function x squared minus the limit as x approaches 4 of the function 2x plus the limit as x approaches 4 of the function 5. Now, I also have a power law, which says that in this first piece, for instance, doing the limit as x approaches 4 of x squared, that's the same thing as doing the limit as x approaches 4 of x and then squaring the answer. And then the limit as x approaches 4 of 2x, that's the same thing as 2 times the limit as x approaches 4 of x. And lastly, this is still the limit as x approaches 4 of the constant 5. Now we've gotten all of these down to those two limits that were guaranteed to always exist. So the limit as x approaches 4 of x is just 4. Then the 2 times the limit as x approaches 4 of x is just 2 times 4. And then the constant 5. But look how similar this is to if I had just taken the function f of x, which is x squared minus 2x plus 5, and simply evaluated it at 4. I would get 4 squared minus 2 times 4 plus 5. And that's essentially the point. These limit laws work in such a way that you can just evaluate the limit for a continuous function, and if you get a real number as your answer, you're done. That's what the limit value is. So this would be, let's see, 16 minus 8 plus 5. So 16 minus 8 is 8, plus 5 gives you 13. So that limit value is 13. Let's try some additional examples. First off, the limit as x approaches 2 of 2x squared minus 1. 2x squared minus 1 is a continuous polynomial function. If I just evaluate 2 times 2 squared minus 1, that's going to be 2 times 4 minus 1. 2 times 4 is 8. 8 minus 1 is 7. I've got a real number. I'm done. That's the value of the limit. You can go through the process of seeing what the x values approach, or seeing what the y values approach as you let x get closer to 2. Limit from the left, limit from the right, you're going to get 7. All right, the limit as x approaches 0 of the square root of x squared plus 4. As long as you're on this square roots domain, you're fine. So let's just see what happens if I put in 0. 0 squared plus 4 would be the square root of 4, which is 2. That works out fine. All right. And next up, the limit as x approaches pi of x times cosine x. So x is a continuous function. Cosine x is a continuous function. So let me just plug in pi and see what happens. So this would be pi times the cosine of pi. And if you're a bit unsure of what the cosine of pi is, just remember your basic trigonometry. So pi is the angle right over here. This point on the unit circle at an angle of pi would be -1, 0. So cosine is the x-coordinate on your unit circle, so pi times -1, which is negative pi. The limit as x approaches pi of tangent squared x. Tangent, as long as you're not using one of the values that leads to a asymptote, is continuous on its domain. So let's see what happens here. So this would be tangent squared of pi as tangent of pi squared, in case you're unsure exactly how that notation works out. So I've already got pi listed here, so if you're unsure of exactly what tangent of pi would be, remember that tangent of anything is sine x over cosine x. So at pi, this would be sine of pi. This would be cosine of pi. So it's going to be 0 divided by -1 squared. 0 divided by anything is just 0. So this results in 0. That's fine. That's a perfectly great limit value. Next up, limit as x approaches 0, e to the negative x times the sine of x plus pi over 4. Probably looks intimidating, but as long as these are continuous, you don't have to do anything all that difficult. And if you happen to be unsure of how these properties work out, if you have your calculator available to you, then just use a table. It'll take more time, but it'll work out. So plug in 0, so e to the -0 times sine of 0 plus pi over 4. So -0, of course, is just 0. So e to the 0, be careful. It's tempting to say 0, but something raised to the 0th power is equal to 1. Even e to the 0th power is equal to 1. So then it's 1 times sine of pi over 4. Sine of pi over 4, that is the square root of 2 over 2. So 1 times that would be the same. Lastly, the limit as x approaches 1 of the natural log of x plus 1 divided by e to the x minus 1. Let's just plug in 1 and see what happens. So it would be the natural log of 1 plus 1 divided by e to the 1 minus 1. The natural log of 1 plus 1 is the natural log of 2. E to the 1 minus 1 is e to the 0. E to the 0, as we just pointed out, is 1. So this is effectively the natural log of 2 divided by 1, which is the natural log of 2. Of course, you could write as a decimal if you wanted to approximate it, but in mathematics, exact answers are always appreciated and preferred. Now, if you plug in the value that is your limit value, and you come up with an answer, you're done. You just get a real number and you're finished. However, if you don't get a real number, if you do happen to run into division by 0, then it's potential that you run into this sort of thing. It's called an indeterminate form. It's 0 divided by 0. 0 divided by 0 is more like a hole in the graph rather than an asymptote. So it doesn't actually mean that it is undefined, but it's potentially something that is able to be evaluated as a limit still. So remember, when we had holes in the graph, we could evaluate limits there, but when we had asymptotes, we could not. So if that limit returns a value of 0 over 0, it doesn't actually give any information to what the value of the limit actually is. But you might have some algebra that you can do in order to still evaluate this limit analytically. So you could go through and use the tables, but generally analytics are usually a little bit faster still. So let's begin with the example. X goes to 4 of x squared minus 2x minus 8 all over x minus 4. You should always try to plug in your value first, just to see what happens. Because if you get a real number, you're done. You don't have to go any further. This would be 16 minus 8 minus 8 over 0, which in fact would be 0 over 0. So that right there tells me that, actually it tells me nothing. It doesn't tell me that the limit exists or that the limit does not exist. It just tells me nothing. It's indeterminate. That's why we call it that. We have to do further investigation. Generally, that further investigation involves doing some algebra. So the limit as x approaches 4 of this particular function would be the same thing as the limit as, well, if we factor the numerator, into, let's see, x and x. If I make this 4 and 2, that looks good. It would need to be a negative 4 and a positive 2, which is great because I have a matching term of x minus 4 in the denominator. Now this entire term, x minus 4, cancels this entire term, x minus 4. I find students still make problems with that, even at this level. Make sure you understand that x minus 4 is just a single number. And you might be confused by that because you're like, x represents a number. Obviously, negative 4 is a number. But when x is determined, when you put in a value for x, you're taking 4 away from that value. So if you put in 6, the number is 2. It's just one number. So it would be 2 in the numerator and 2 in the denominator. The 2 cancels out the entire term, the entire bit, x minus 4. Okay? Now that leaves me with the limit as x approaches 4 of x plus 2, a seemingly new function. And this function, what's important about it is I can plug in 4, and it would be 4 plus 2, which would give me 6. And now I have a real number as an answer, so I have evaluated this limit even still without using a table or a graph. So if you run into 0 over 0, there's still a chance that you could do these algebraically. And oftentimes that's what your instructor wants you to do. But if you don't know the algebra involved to get to the answer, then certainly using a table would at least give you the result that you need. Let's look at another one. So limit as x approaches 0 of the square root of x plus 9 minus 3 divided by x. Here, if I put in 0, 0 plus 9 minus 3 over 0 would be, well, the square root of 0 plus 9 is the square root of 9, which is 3, minus 3 over 0, I have 0 divided by 0. So that means there should be some sort of algebra that I can do in order to turn this into a limit that I can actually work. So let's see. When it comes to polynomials, generally factoring is the way to go. When it comes to square roots, it is most likely going to be something of the form of conjugates. So if I multiply the numerator and denominator by the conjugate of the numerator, and a conjugate is just the binomial, when you have a binomial term and you switch the sign inside the binomial. So the conjugate of x plus 3 is x minus 3. The conjugate of x minus 2 is x plus 2. So you just take the same two terms, but you switch the sign between them. The reason that you might do that is because of the difference of squares. So in this case, the difference of squares is set up. So let me come down here and I'll do that. So in the difference of squares, you have a plus b times a minus b. If you FOIL this out, it becomes a squared minus b squared. So if a happens to be the square root of x plus 9, sorry about that, and b is 3, then you're still, when you FOIL this out, going to end up with a squared, which would be, in this case, the square root of x plus 9 squared, minus b squared, which would be 3 squared. When you square a square root, the square root disappears. Now 3 squared is just 9, so the result here is just simply an x. So all the algebra involved here results in just x for the numerator, and then you have x times the square root down there in the denominator. But this x in the numerator cancels this x in the denominator, which is what you're looking for, is some sort of cancellation. So then that's the limit as x approaches 0 of 1 over all this. So that's going to be 1 over the square root of 0 plus 9 plus 3, which would be 1 over 3 plus 3, or 1/6. And that's perfect. Now you have the limit value. Now, it's usually at this point where I get somebody asking me, do I need to write the limit every single time as I'm going through this process? And the answer is yes, you absolutely do. Because it comes down to, when you say two things are equal in mathematics, you're saying that they agree 100% on an infinite scale from negative infinity to positive infinity. So the limit of this function is a single number when x approaches 0. If you try to omit the limit part here and just say this is equal to x over x times this function, you're trying to say this right here, which is the number 1/6, is equal to this function over here, which is not the number 1/6. Those two things do not agree with one another. So you absolutely can't omit the limit as x approaches 0. The only time that you can finally omit it is when you take that limit, which means to put the limit value in for x. At that point, you can remove the limit notation, not before. If you want to go off to the side like I did down here, and do your algebra off to the side and then bring it back to your limit, that's fine. But don't say that this is equal to this without the limit. It's just not equal. So be very careful in that notation. Next, we have an example of the limit as x approaches 0 of 1 divided by x plus 5 minus 1/5 all over x. First thing we should always begin with is seeing if we plug in the limit value, if we get a result. So this would be 1 over 0 plus 5 minus 1/5 divided by 0. So that's 1/5 minus 1/5 divided by 0, which results in 0 divided by 0. So that tells me that there's probably some algebra that I can do. And when it comes to fractions, generally what I need to do is something of the form, and let me come down to the bottom here. So 1 over x plus 5 minus 1/5 divided by x. So I need to multiply by something over itself to get rid of these complex fractions. Generally what you need is whatever the least common multiplier is of the denominators. So I'm going to multiply everything through by 5 times x plus 5. Alright, so if I multiply this term times the fraction 1 over x minus x plus 5, the x plus 5's cancel. That leaves me with the factor 5. If I multiply that same times 1/5, the 5's cancel and leaves me with x plus 5. In the denominator, it's going to be 5x times x plus 5. So, simplifying, this would be 5 minus x minus 5, because that negative would distribute to both terms inside these parentheses. And this is still 5x times x plus 5. These 5's cancel, which leaves me negative x over 5x times x plus 5. And if you'll notice, this x and this x are now going to cancel. So I have, after all that algebra, the limit, as x approaches 0, of negative 1 over 5 times x plus 5. And if I plug in 0, everything should work out now, because once you get that term in the numerator and denominator to cancel, that's usually where the 0 over 0 comes from. So let me plug in 0 now. It's negative 1 times 5 times 0 plus 5, or negative 1/25. And I have an answer now. This next example, if I plug in 0, I would have 4 times e to the 2 times 0 minus 1 over e to the 0 minus 1. Should be 4 times, so e to the 0 is going to be 1, because anything to the 0th power is just 1. So I have this term 1 minus 1 in the numerator and denominator, cancels, and therefore those things equal 0 over 0. Now, that tells me there is some algebra that can be done. So when it comes to working with exponents, one thing that we can do, for instance, e to the 2x, we can think of as e to the x quantity squared. So that when I have, I'm going to do my algebra down here, 4 times e to the 2x minus 1 all over e to the x minus 1. I can make this 4 times e to the x, whoops, let me try that again. E to the x squared minus 1, oh, that's now a bracket, all over e to the x minus 1. In the numerator, these brackets are the same thing as a set of nested parentheses. All it's telling me right now is I have the difference of squares. I can make this e to the x plus 1 times e to the x minus 1. That's what that factors into. So then I have this term of e to the x minus 1, both the numerator and denominator, which cancels. So this is 4 times e to the x plus 1. So this would be the limit as x approaches 0 of 4 times e to the x plus 1, which would be 4 times e to the 0 plus 1 when I evaluate the limit, 4 times 1 plus 1, or I get 8. Now you may be thinking, that's not algebra that I'm aware of. And that would be okay. You can still evaluate limits for functions using prior knowledge. So for instance, if you used your calculator and for your function y you put in 4 times e to the 2x minus 1, and the e to the 2x minus 1 is in parentheses, divided by, then in parentheses for the entire denominator, e to the x minus 1, e to the x, and then minus 1 on the outside of those parentheses. Sometimes in the calculator these parentheses get a bit hairy, but the thing is, anything in parentheses, or anything as exponents goes in parentheses, anything around denominators or numerators should go in parentheses. Since it's 4 times those parentheses, you don't technically need something around the 4, but if you want to be safe, you can put a second set. Now, let's go to the table. If I start putting in values on my limit number, which is 0, if I put in 0, I get undefined, so I can't just plug in 0. But if I put in, say, negative 0.1, negative 0.01, negative 0.001, and so forth, look what's happening. I'm getting closer and closer to 8. If I put in 0.1, 0.01, 0.001, and so forth, oops, I'm getting closer and closer to 8 on the right-hand side as well. So that means the limit from the left and the limit from the right agree and are equal to 8, so the limit itself is equal to 8. So if you don't know the algebra, you can still use your calculator if your instructor permits. Next up, a limit that does not exist. Okay, so far all the ones we've done have existed through some sort of algebra. So here's the thing. If I plug in the limit point, I would get 2 divided by 4 minus 4, which is 2 divided by 0. That's an asymptote. It's not an undefined value. 0 divided by 0 is undefined. Some number other than 0 divided by 0 is defined. It's an asymptote. This limit does not exist. The only way that you might be able to say something a little bit more about it is if on both sides of the asymptote your function went to positive infinity, or on both sides they went to negative infinity. But otherwise, this limit is not undefined. It's absolutely defined. It's an asymptote. It does not exist. Let's look at a one-sided limit then. Okay, so if I plug in the limit value, this would be 2 over 2 plus 2, which is 2 divided by 4, or 1/2. So that's a real number, and that's great. What that means is the limit exists and is equal to this real number. When a limit exists, it implies that the limit from the left and the limit from the right both existed and agreed with one another. So even though you only really wanted to know the limit from the left, that's okay in this case because both the limit from the left and the right equal 1/2. So you've got the limit from the left already. So you can proceed in the same way here as well. Now here's one where the limit laws do not apply. The reason that they don't apply is because if you try and plug in 3, you would have 1 over 3 minus 3, which is 1 over 0, and then 4 over 9 minus 6 minus 3. So you have 1 over 0 minus 4 over 0. So individually, these two limits do not exist. However, it doesn't mean that the overall limit does not exist. It's just saying, like the limit laws, they apply when you have functions that are continuous and exist. When you have functions that are not continuous and don't exist, the limit laws don't apply, but that doesn't tell you that the limit doesn't exist overall. Let's try it out. So let me go off to the side and do some algebra. This would be 1 over x minus 3 minus 4 over, I'm going to factor this denominator, x and x, 3, 1, if it's negative 3 and positive 1, that's great. All right, so what I need to do then is multiply this first fraction by x plus 1 over itself, so that I have x plus 1 minus 4 all over the common denominator of x minus 3 times x plus 1, which gives me, whoops, which gives me x minus 3 over x minus 3 times x plus 1, and I have a factor of x minus 3 in both the numerator and denominator, which cancel away. So 1 over x plus 1. So all of this is the same limit as x approaches 3 of 1 over x plus 1. If I plug in 3, it's 1 over 3 plus 1, which is 1/4. So the limit actually did exist through some algebra. It's just the limit laws weren't going to tell us anything until we did some simplification first. The last thing that I'm going to do with these analytic limits is the difference quotient. The difference quotient is a limit that looks like this. It's the limit as delta x goes to 0 of f of x plus delta x minus f of x all over delta x. And this thing has a particular importance in the study of calculus, which we'll look at it, what it means later in the course, but for now we just want to learn the mechanics of how to evaluate it. So let's start with a function 2x minus 5. Now first off, this delta x business. So delta x, like this right here is the Greek letter delta, this is x. This is something that we use a lot in calculus, which means the change in x. It's one single variable. It's just observing how a variable is changing over time. So it might move 2 units to the left or 3 units to the right or something like that. It's just how it moves. But just know that it's a single number, okay? So it's just one single variable. To lessen the confusion, a lot of times what textbooks will do is replace delta x with h instead. I prefer not doing that simply because delta x is an important number in calculus, and so I want to stick with the notation that you're going to run into later on in the course. So this limit, we need to figure out f of x plus delta x and take that minus f of x. So that's going to be our first situation. So f of x plus delta x. So our function f is like this. So the x itself is kind of like a magic box, if you want. And whatever you put into one magic box, the same thing appears in all the other magic boxes. So if I put a 4 in right here, 4 magically appears over there, and that's what it means to evaluate f of 4. And if I put a bit more, a bit larger construct, if I put like x minus 1 here, x minus 1 appears over there. So whatever I put in this box just appears in all these other boxes. It just so happens that right now what I'm going to do is put x plus delta x. So x plus delta x is going to show up over here in this one. So this means 2 times the quantity x plus delta x minus 5. And simplifying, that would be 2x plus 2 delta x minus 5. So f of x plus delta x, that becomes 2x plus 2 delta x minus 5. Okay? Now, f of x is a bit easier. We already have what f of x is. It's the original function, 2x minus 5. So I evaluate the function at x plus delta x, then I subtract the original function from it. And then when I do my limit, I'm going to take all of this divided by the quantity delta x, and that's just right up here from the formula. So it's f of x plus delta x minus f of x divided by delta x. So what I'm looking at right now is the limit as delta x goes to 0 of 2x plus 2 delta x minus 5. I'm going to take away the parentheses here, so I'm going to distribute the negative and make it minus 2x plus 5 all over delta x. So in the next step, I still have a limit to calculate. So as delta x goes to 0, in this particular situation, I have a negative 5 and a positive 5 which cancel, positive 2x and negative 2x which cancel. So that leaves me with 2 delta x over delta x. And remember, delta x is one quantity, so when you have one quantity over the same quantity through division, those will cancel out. So this is effectively the limit as delta x goes to 0 of 2, and the limit of a constant is just the constant itself. So the result here is 2. Okay, so it takes a few examples and trials to get used to, but it's really not all that bad. One thing that you need to understand is that sometimes, however, this doesn't result in simply a number. Sometimes it results in a function. And that's why it's important to be able to do your limits analytically with the techniques I've given you today. Yes, when you are evaluating a limit at a number, you can always come up with an answer using your calculator. But when you're doing difference quotients, you almost always end up with a function, and your calculator is not going to be any help to you. So let's try the difference quotient for this function and see what happens. So the difference quotient is the limit as delta x approaches 0 of f of x plus delta x minus f of x divided by delta x. Let me go off to the side and figure out what f of x plus delta x is. So I'll just come off over here. F of anything I put in these parentheses is going to be whatever that thing was squared minus 2. So when I put in x plus delta x, I'm going to take that x plus delta x and square it, then subtract 2. So this would be x plus delta x squared minus 2. Simplify things as much as you can. So let's expand this binomial. It would be x squared plus 2x delta x plus delta x squared minus 2. And what I did there is the process of FOIL. So if you're uncertain how that works out, walk through the stages of FOIL and verify that you get the same result. Okay, so now this limit, I might need a little more space. Let me do this. This limit is going to be the limit as delta x goes to 0 of all this that I just found. So x squared plus 2x delta x plus delta x squared minus 2. Then I subtract the original function, which is x squared minus 2. Put that all over delta x. Now at this point in the process, if you've done everything correctly, you should get a lot of stuff that cancels out. The first thing I'm going to do is distribute this negative this way. All right, so it's going to be x squared plus 2x delta x plus delta x squared minus 2 minus x squared plus 2 all over delta x. So that this x squared cancels that one. This positive 2 cancels that negative 2. Leaving me with the limit as delta x goes to 0, 2x times delta x plus delta x squared all over delta x. Now, there's a shared factor of delta x in the numerator and denominator. Be careful when you cancel that away, because the way that actually works, you can factor out delta x from each term in the numerator, leaving you delta x times 2x plus delta x, which can cancel out the delta x in the denominator. What I find students doing improperly, if you don't do it the way I just did, is they'll try and say, oh, here's a delta x and there's a delta x, I'll cancel that out. But then you still have a delta x squared term where you were supposed to have a delta x term. What you have to do properly is, when you have a polynomial in the numerator divided by a monomial in the denominator, is every term in the numerator has to be canceled out. So the square basically cancels out with the denominator. That you can do, but I think this method over here is generally a bit safer. However you want to treat it is fine, of course. That leaves me with the limit as delta x goes to 0, 2x plus delta x and as I let delta x go to 0, that results in 2x plus 0, which is 2 times x. So the result here is a function, not a single number. So your calculator can't help you with this type of a result. It doesn't have any means of coming up with an answer of 2x rather than just 2.